Well, good morning. We have a little bit of snow on the ground here in the Seattle Redmond area, which causes the entire city to come to a grinding halt. So while I wait for the traffic to clear up a little bit so that I can get into the office, I thought I'd whip in a little video on crystal detectors. Here I have three crystal detectors. This guy here is an 8470B. This guy is an 8472B. And this guy here is an 8473C. And they're all low barrier Schottky diode detectors. This guy is an N-type and goes from 10 megahertz to 18 gig. This guy is an SMA or an APC35 SMA and goes from 10 meg to 18 gigahertz, and this guy here is a APC35, and it goes from 10 megahertz to 26.5 gigahertz. Now, these are great and very useful little devices here because what they enable you to do is to accurately measure and to accurately level and control the output, or to characterize the output of a signal generator, of an RF signal source across a broadband sort of spectrum. They're also very useful for working out the SWR of a device, because you can put modulation on a signal, and then what we'll be able to do is detect the modulation at the other end, and you'll be able to see that. So typically what you would do is take these devices and plug them straight into a cable. Now, I have my 8340B set up here. It's still in the process of being tweaked and calibrated, but it's working now, and it will cover. So focus more, when we start seeing some of the waveforms, focus more on just the general concept of how the waveform's laid out than the specific details of the waveform itself, because we're still looking for that to be calibrated. But I wanted to use it because it has a very handy sweep out output on the front of the actual generator, so I didn't need to pull out my cabinet and put a cable in on the sweep out on the back of some of my other generators to get up to 26.5 gig. So with that, let's take a quick look at some of the characteristics, or how these things are actually used. So typically you'd see these guys being used in their square law region. So let's zoom in a bit just so you can see that. And so what you'll see here is typically these detectors will be used in this square law region, which will be, if you look at the output voltage versus the input power, the square law region is where there's a linear response, and effectively the output voltage of the detector follows a square power approach to the input RF power that's in there. So you can get a accurate sort of linear work back and forwards, and typically that's sort of like minus 15 to minus 30 odd dB. It's about this sort of region here. And then what happens is, as you start to increase the power, these things start to roll off, and they'll get out of their square law region. And you can see the typical sort of detector square law response. You basically get a 0 dB impact on the signal, and you can play around with the output load, the impedance, to change the curve. But fundamentally, once you start getting around, if you look at 50 ohms, which is this guy here, once you start getting around the 20, the minus 15 sort of dB M range, you're starting to deviate from the square law approach here. You can go and get some additional options of this, which will give you better square law. In fact, if we have a look at the back of this guy here, you can see that there are. Let me see if I can zoom in a little bit closer. See if we can get the. There we go. You can see that what you'll get is options for the changing the a matched pair of diodes that'll be in here. You can get the load. You can get positive and negative, and then different types of things here. These guys have, if we have a look at the back of this guy here, where am I? There we go. You can see similar sort of options, a pair, match pair, positive, and then option 100, which I don't know what that is. But basically, the biggest option that you'll get most of the time when you're buying these from eBay is you'll find these will come out as negative devices. This guy happens to be a positive, but mostly these guys, like these two units here, are negative option, and we can see here that you know, this is they just mark this guy as standard, but these are basically you know, going to have a voltage, and as you increase the power, you're going to see the apparent or the output voltage that will come out to your scope at the other end will go negative, whereas with this guy you'll see the inverse of that. You'll have a baseline and the voltage will go positive as the power increases. In most cases, when you're using these for things like external leveling, most of the circuits on the sweep, on the synthesized sweepers, don't really care whether it's positive or negative. You know, they are basically just simply matching a voltage and then keeping it there. And what you're basically doing is, let's grab a little bit of paper here. What you're basically doing is, you're taking your sweeper and you're sending it out. Let's zoom in a little bit so you can see what I'm writing. So you're taking that and then you're putting that into, one of those classic sort of 1166-7A splitters, and that's coming out to some form of detector that might go into a power meter like a 438A, and then over here this is coming out and this is going into your device under test. And what you're actually going to, actually no, hang on, let me rephrase. This is coming out and going into the crystal detector, and this is coming back and going back into the sweep generator. And when you've done this, you typically will then set your output power based off this reading here, and so you want to get a particular power at the particular frequency. And this can be great because the cables can be very, very long and stuff like that, but you've basically got your ALC loop, covers that whole piece of kit here. And then what you do is you break this connection here and you take that out to your device under test, and now the ALC here in the sweeper will keep the voltage set, the power output set, whatever dBm that you had on your 438A or your power meter or whatever method you use to actually set the power. So this is like how you will see these a lot of the time. And in fact, for my 8340B, you used it you would use this to keep the power level constant, and then when you were putting it in pulse mode, where you were generating pulses of power, you would utilize this approach to keep the pulse level set. And there's an entire document on the Keysight site on externally leveling these devices. So that's one of the experiences that you'll have with them. The other one that you'll have is basically to go and measure SWR and stuff like that. So what you'll do is you'll have a signal generator of some form, and you'll have coming out of here, you'll put an AM modulated, say 1 kilohertz signal, and you'll come into your SWR bridge, and you'll connect to the the device under test, and then from your SWR bridge you'll take it out, you'll take the return value out here to a device like a 415E, and this will show basically the 1 kilohertz signal, and this meter is set up and designed to show that 1 kilohertz signal as a function of the SWR values that will come in. You'll come in here and then you'll set this with a short or an open, and then you'll tweak the meter to get the reference level correct, and then once you've done that, then you'll connect your device under test, and this is basically a very, very sensitive 1 kilohertz a tuned amplifier, and you'll see the SWR value on the graduated meter scale. And so that's another use for the detectors. Basically, at this point, the detector here, the 415E, doesn't care what frequency you're putting through here. It's just reading that 1 kilohertz amplitude modulation, because the actual diode detector is handling the frequency range that you've got. So that's some examples of these things. You can see the typical equivalent diode model is here. This is a great this is basically the crystal detector overview document. You can see down here the typical SWR of these devices, up to about 26.5 gig. You're operating pretty well under an SWR of 1.3, so it's a good match for the unit across that range. So let's take a look at these in operation. We'll start with our big guy here, and we'll start with the big guy here, and see what it looks like on my with the signal generator turned on. Okay, so here we are. We have the sweeper set up, and you can hear it running. The sweep out is coming into channel 4 here, and that you can see as it sweeps through the 4 bands that the 8340B has, from 10 megahertz to 26.5 gig. It's the morning, so the drink of choice is a nice coffee. Anyway, the first guy we're going to look at is the 8470B, and this guy is actually a 10 meg to 18 gigahertz. So while the sweeper has 4 bands, it's actually set to only sweep from 10 megahertz up to 18 gigahertz. So let's put the little adapter in that will let me connect to the SMA cable that I have coming out here. Now, it's important not to look at the absolute values of what we're getting on the outputs here, because of 2 reasons. One, the 8340B hasn't finished its calibration. I'm still working on tweaking it, getting things in line. The other thing is that I have like 6 or so feet of cable connecting it, so you're going to get signal loss towards the upper end of the spectrum as it sweeps. Okay, well, that was Comcast telling me that I've hit my data cap, which isn't surprising. I did a lot of reinstall and backup stuff and so on. So anyway, where was I? You can see here that now that we have this in, you can see this is the positive voltage that's coming out of the system here. And if you imagine that all of these points were all together, you would see a curve effectively that shows how the whole power is, falling off towards the upper 18 gigahertz range. But as each step occurs, each little sweep goes on, and then it pauses, then it sweeps, you'll see you can see basically the curve in power that's being reported, the voltage is coming out of the item here. So let's go and take a look at the next guy, and you'll notice that even though they're different detectors, it's the same sort of experience. So let me just put that aside. Let's grab, we'll go with this guy again, and he's also an 18 gigahertz detector. And when we put this in, what you'll see that this is a negative one, and so you're seeing that the line's coming down there. Now let me just go to storage, and we'll move that, and we'll just go in here and we'll select this guy and we'll load him, and we'll change the setups. And you'll see now that it's a negative coming down. But basically, if you look in close, you can see that same curve. Now, that's characteristic of all these detectors and characteristic of the setup, because you're going to have more losses as you go through and use these detectors. So let's put the last one in, And this one is designed to go to 26 and a half gigahertz. So this is a little guy here. Let's put this on here. Let me change the stop frequency to 26.5 gigahertz. And let's load the setup that I saved for this guy. I always keep pushing the select button, rather than coming back to the load, because it's sort of the other buttons are pushable. And here you can see, that same sort of thing. So that's, giving you an example of just reading this absolutely directly. The other way you would use this is to go and look at the spectrum and say, I want to characterize this spectrum or look at this in correlation to this sweep time that occurs. And so how you would do that is utilize the XY mode on your time base here. You would just go change this to XY mode, and then you get this view. Now I've already set this up because it took a little bit of, you had to go and screw around a little bit with it to get everything set correctly. So let's just go and load those because we already set that up. Okay, and so for whatever reason it doesn't save the trigger here, so it jumps around a bit. But now that we've correlated this for the sweep and the dwell times, you can actually now really see that roll off as we change as we go through the various sections. You can see each of the band amplitude markers here where it drops down to 0, and we run across the band there. But this gives you a way now of looking at that broadband signal, which is pretty cool. Now, that view is what I used when I utilized this guy to tune the lower bands on the 8340 to try and bring it back into working where I was getting an unleveled power issue. And you saw it turned out that solving it required me to update the calibration constants. But now I have a couple of little excursions in it, so we'll go back with the 26.5 gig and tune those back out. But you're getting like a nice sort of signal here, and this is how you would go use it. So let's take a look at, see if we can set up for that AM signal. So I'm going to go modify the signal generator, and then we'll come back and look at how we're getting the AM signal on the oscilloscope. All right, right back. All right, so here we are. We have our little crystal detector set up, and you can see that we're just reading the value coming out of the crystal detector. So it's showing the pauses, it's showing the basic curve, and we're not. I'm not triggering on the sweep here. So you're just getting what you're getting here. Now, why would you do this? Well, imagine that I had my generator set up for 10 gigahertz, right? That my scope here clearly is a Rygold 1054, so it can't handle 10 gigahertz. So for me to go and see that signal, I couldn't possibly do that. If I put this into an SWR bridge and was trying to read the SWR of the reflected energy, again I couldn't do this because the signal coming back would have the same frequency as the signal going in. But what I can do is I can set a single frequency here and then set amplitude modulation. And what we'll see here is we'll see the change in effect. So let me go to manual, and here now I have a single value set, so we're getting 10 megahertz out of this. If I put 10 gigahertz in, I have 10 gigahertz set now. Sorry, I was reading the wrong display. So we're seeing this, and we're seeing a single value because it's a single frequency with single power coming into the detector. If I now turn amplitude modulation on, now you're going to see that there's a signal coming in there. So if we step this up a little bit, and then come in and let's take channel 1, let's AC couple that, and then step that up, step that back. Yep. Where's our trigger? There we go. Now I've got a stable signal here, and so if I actually, if I step the frequency in a bit, and I turn on measure and I turn on the hardware counter, you can see that I'm getting a 1 kilohertz signal in there. And so now I can actually, measure the amplitude modulation. I can measure the size of the signal coming back regardless of the frequency, and I don't necessarily need to have a measurement device that is capable of measuring the full spectrum of the power that's coming there. So that's one of the cool things about utilizing these crystal detectors. We'll see that in a little bit more. I have another video I want to do on actually reading SWR and utilizing a crystal detector to go do that. And so we'll take a look at that sometime in the future. I don't have it set up yet. Anyway, I hope you found this interesting, and we will catch you later. Bye.